The Java happens before guarantee is a set of restrictions on instruction reordering to avoid instruction reordering breaking the Java visibility guarantees. By the way, I assume you are somewhat familiar with the basics of the Java memory model already, more specifically the thread stacks and the heap and how Java threads use these two. If not, I would recommend that you watch my video introduction to the Java memory model. I have included a link to that video in the description below this video. CPUs can execute multiple instructions in parallel, provided that these instructions are independent of each other. And if you look at the example here on the left, I have shown you an example where the instructions are not independent from each other. You can see the second instruction uses A, which is the result of the first instruction. So these two instructions cannot be executed in parallel. And the same is true in the second set of instructions here, where the second instruction here uses F, which is the result of the first instruction. So these two instructions can also not be executed in parallel. But these two could be executed in parallel, right? Because F equals G plus H does not depend on anything from the instruction D equals A plus E. In order to increase parallelism, a CPU may look ahead at future instructions to see if any of them can be executed in parallel with the one that it is currently executing. So if you look at the example here, you can see if it starts by executing this instruction here, it realizes it cannot start this instruction because this depends on the output of the first instruction. But then it gets to the third one and realizes this instruction here does not use any of the results from the two first instructions here. So this instruction could be executed in parallel with the first instruction. And thus, even if the instructions are listed in this exact order in the program, they may get executed out of order because the CPU looks ahead at future instructions in order to find instructions that can be executed in parallel without breaking the semantics of the program. To make the CPU's job easier, the Java compiler and the Java virtual machine may reorder instructions already at compile time. And that means either when your Java program is compiled into bytecode or when the bytecode is compiled into assembly language instructions by the Java VM's JIT compiler. In this example here, you can see that the original order of the instructions as shown here on the left has been changed over here on the right. The Java compiler has detected that these instructions here can be executed in parallel and that they are independent of each other, and therefore instead of having the instruction executed here, it has been moved up here. So now these two instructions can easily be executed in parallel by the CPU. And the same is now true of the second set of instructions here. This instruction can be executed in parallel with the last instruction here. And so now the execution job has been made easier for the CPU. It does not have to look ahead in the instruction pipeline here to find an instruction it can execute in parallel with the other one here. And that again makes the execution of the whole program faster. Unfortunately, instruction reordering may affect the correctness of multi-threaded applications where the threads need to communicate via shared objects. Throughout the rest of this video, we will look at how instruction reordering may affect correctness of such multi-threaded applications and what the Java happens before guarantee does to fix that. Imagine an application that has two threads running on separate CPUs and where thread 1 produces frames to be drawn on the screen and thread 2 consumes these threads and draws them on the screen. The two threads communicate through a shared instance of this frame exchanger class, which I have shown you here in the middle. Thread 1 will continuously call store frame and thread 2 will continuously call take frame. Now the implementation here is not very well designed, but that is on purpose. That is in order to be able to illustrate some of the problems which the Java happens before guarantee will eventually help us solve. The shared frame exchanger instance is stored in main memory, but during execution the two threads make copies of the fields of the frame exchanger instance, and these copies are stored in local CPU registers and caches here. And to illustrate that, I have moved the code of the frame exchanger out under the threads here in both sides. Just keep in mind that even if not explicitly illustrated here, even if it looks like there are two copies of the frame exchanger class here, there is actually only one, and it is stored here in main memory. As explained earlier, the intention is that thread 1 calls store frame, providing a frame as parameter to the store frame method, and this frame then gets stored internally in the shared frame exchanger instance. And thread 2 then calls take frame and takes this newly produced frame and draws it on the screen. However, since neither of these fields here are declared volatile, and because neither store frame or take frame contains any synchronized blocks, there is no guarantee that the changes made to these fields in the frame exchanger here, in the local copies of the frame exchanger fields, are visible to the other thread. In order to be visible, two things has to happen. First of all, the thread here that makes changes to the local copies of these fields must flush these updates to main memory. Second, the other thread that reads these fields must read them from main memory. It is not enough that it just uses its local copies here, because then even if thread 1 here flushes the changes to these fields to main memory, if thread 2 never reads them again from main memory and only uses its private copies here, its local copies, then the changes made by thread 1 will not be visible to thread 2. So this implementation here has a visibility problem. If you check out the description below this video, you will find a link to my Java memory model video, which explains this visibility problem in more detail. To fix the visibility problem, we can declare the fields volatile. As you can see, I have done that in the code here, inserted the Java volatile keyword here. And when a field is volatile, that means that every write to the field will be flushed directly to main memory. The values set will be written directly to main memory. And similarly, whenever a volatile field is read, the value of the field is read directly from main memory. This way, the changes written to these fields by one thread will be visible in main memory and will be read by the thread reading the same fields, because they are read directly from main memory. Because of the Java volatile visibility guarantee, it is actually not necessary to declare all of the fields here volatile. The volatile visibility guarantee says that at the time you write to a volatile variable and that value is written directly to main memory, all the variables that are visible to the thread writing to the volatile variable will also get flushed to main memory. So in this case here, you can see that only hasNewFrame is declared volatile. And inside of store frame, we first write to this .frame and then this .frame stored count, and then to this hasNewFrame. And at this time here, at this point in time, all of these fields are flushed to main memory, not just the volatile field. Actually, all of these are flushed as well. The Java volatile visibility guarantee also says that at the time you read a volatile variable, the values of all variables visible to the thread reading the volatile variable will also get refreshed from main memory. So if you look at take frame over here, as you can see, we are reading hasNewFrame inside of a while loop. And because of that, that means that for each loop in here, we are reading has new frame from main memory, and at that time we also refresh frame stored count and also frame. Down here at the bottom you can see that we are writing again to has new frame, and because has new frame is volatile, that means that all of the changed variables here, all the variables will get flushed again to main memory. And it is only required that the fields that have actually changed are flushed back to main memory. You do not need to change or to flush a field that has not been changed. I mean, why would you need to do that? So in this case, we know only frames taken count has changed and has new frame has changed. So these two are guaranteed to be flushed back to main memory. Now that we have a visibility guarantee of has new frame and these other variables here, we are certain that thread 2 will not spin in this while loop forever. Eventually thread 1 will change the value of has new frame to true in the store frame method, and this while loop here will exit, and thread 2 will see the frame and take the frame that was set by thread 1 and return that from take frame. To CPU 1, the instructions inside of store frame look like they are independent of each other, right? None of these variables depend on, none of these instructions here depend on the result of any of the other instructions. And that means that to CPU 1, it looks like it is allowed to reorder the instructions inside of store frame. However, if we do that, this might affect the visibility guarantee of the method. Let's look at what happens if the CPU reordered the instructions so they were executed in this order. Now the write to the volatile variable happens at the beginning of the method, and that means that at this point in time the value of has new frame is flushed to main memory along with whatever is stored in the other variables or the other fields here at that time. And that means that the two subsequent writes to frame and frame stored count are not guaranteed to be written to main memory at this point, because after we have finished writing to the volatile variable, the next time we are guaranteed to have the values of these variables flushed to main memory is the next time we write to has new frame, which will happen the next time store frame is called. So the result of that is that even though thread 2 will still correctly exit this while loop sooner or later, the value that it is reading from this frame here, this frame field here, could be the value of the frame field as set in the previous call to store frame, right? Because after all, when we flush the values of has new frame here, then we have not yet set the new value of frame, and which means at this point in time we might be flushing the old value here, and that might be what thread 2 is seeing. It could also be, there's no guarantee that this is what will happen. It could also be that somehow the write to this frame here is actually flushed to main memory, and so that thread 2 actually sees the new frame, but there's just no guarantee that this happens, right? Whereas in this ordering here, we have a guarantee that once has new frame changes to true, this dot frame will point to the latest frame set by thread 1. And so as you can see, instruction reordering may break the visibility guarantee of the store frame method. In order to fix the problems with that potential instruction reordering can cause with regards to visibility of volatile variables, Java has introduced the volatile happens before guarantee. And there's a guarantee both for writing to volatile variables and reading from volatile variables. And I will start over here on the left by explaining the happens before guarantee related to writes to volatile variables. So any write to a field or variable that happens before a write to a volatile variable will remain before a write to a volatile variable. So none of these two instructions here can be reordered to happen after the write to has new frame, because has new frame is declared volatile, as you can see up here in this line. These two instructions can still be reordered among themselves. So this instruction could be reordered to occur before this instruction up here, but they cannot be reordered to happen after this write to the volatile variable. Similarly, any read of a volatile variable that is located before reads of other non-volatile or volatile variables are guaranteed to happen before any of these subsequent reads. In this particular case here, it means that the read of has new frame inside here of the while loop here cannot be reordered to happen after this read down here. In other words, the read of has new frame is guaranteed to happen before the read down here of this dot frame, and that is because has new frame is declared volatile. Now, in this particular case here, reordering the instructions so that this read of this dot frame happens before the while loop would completely change the semantics of the methods of the method here. So this reordering is not actually allowed. But in case this had just been a normal read of has new frame here and not happened inside a while loop, inside the condition of a while loop, then even then reordering the instructions so this dot frame, the read of this dot frame here would happen before the read of has new frame would not be allowed. And that is the Java volatile happens before guarantee that puts that restriction on instruction reordering for volatile variables. Java has a similar challenge around instruction reordering around synchronized blocks in Java, and in order to illustrate these problems, I have created a new example here. It is similar to the previous example. You have two threads which are exchanging values through a value exchanger, and there will be a single instance of the value exchanger stored here in main memory, but each of the threads might keep local copies of the values inside of this value exchanger instance during execution. Thread 1 here will call set values, set and with the values object here as parameter, and that will copy the values of the values object inside these three local or private fields. And thread 2 will call get, providing a values object into which the values of these three private fields is copied. The Java synchronized blocks visibility guarantee says that when a thread enters a synchronized block, like for instance over here, the thread will refresh all variables that are visible to the thread at that time, and it will refresh them from main memory. So when thread 1 enters this synchronized block here inside of set, it will first refresh all the values of val A, B, and C from main memory. And after that, it will copy these new values from the values object here into these fields. And when it exits, when thread 1 exits the synchronized block again, all variables visible to the thread will get flushed back into main memory. So at this point in time, val A, B, and C will be flushed to main memory. As you can see over here, we have a similar situation when thread 2 calls get. By the time it enters this synchronized block here, it will refresh the values of val A, val B, and val C from main memory from over here. So it sees the values that were written by thread 1. And at the time the thread 2 here exits this synchronized block, any changed fields would be flushed back to main memory. However, in this particular case, we are not really flushing anything we're not really changing anything inside of value exchanger. We're only changing something inside of this V object here. So it is not so important that they're flushed back, but they will be flushed back, whatever was changed. Now imagine that the instructions in these two methods were reordered, right? So that this assignment here to val C was reordered to happen outside of this synchronized block here. And the read of val A was reordered to happen outside of the synchronized block over here. Now, this reordering would change the visibility guarantees of the code, right? Because by the time thread 1 exits this synchronized block here, only val A and val B have been changed. And so by the time the values of all these three variables are flushed back to memory, only val A and B reflects the new values from V. When we assign a value to val C later on, there's no guarantee that this will get flushed back to main memory, at least not until the next time thread 1 exits this synchronized block here. Now it could be flushed back to main memory, but there's no guarantee that it will be. And that means that now val C may not be correctly reflected in main memory. Similarly, when we are reading val A here, val A here, this dot val A may not yet have been refreshed from main memory. So this could be an old value that we are reading from val A, right? Whereas when we enter this synchronized block here, then we are refreshing the values of val A, B, and C from main memory. And thus down here we are assigning the correct two values to val B and val C, but val A could actually be assigning a wrong value. And actually val C could even be assigned a wrong value too, because of the reordering that happened over here. So val C may not be correctly flushed to main memory. So even if we are reading the latest value of val C from main memory, what is stored in main memory would still be wrong because of this reordering. So as you can see, instruction reordering around synchronized blocks may break the visibility guarantees provided by these synchronized blocks. In order to fix these problems regarding instruction reordering around synchronized blocks, Java synchronized blocks also come with a happens before guarantee. And the happens before guarantee of a synchronized block is, first of all, that any write to a variable that happens before the exit of a synchronized block is guaranteed to remain before the exit of a synchronized block. So this write here, none of these writes here can be reordered to happen after the exit of this synchronized block here. And this also counts for writes to variables that would happen before this synchronized block, right? If two of these writes were happening outside of the synchronized block, they could still not be reordered to happen after this synchronized block exits. Similarly, for reads, the entrance to a synchronized block that happens before a read of a variable is guaranteed to remain before any of these reads to variables that follow the entrance of the synchronized block. So in other words, none of the reads here of these variables here could be moved or reordered to happen before we enter thread 2 enters this synchronized block over here. And that would also be true of reads that happen after the synchronized block here. They cannot be reordered to happen before this synchronized block here is entered. So to summarize, a write that happens before the exit of a synchronized block cannot be reordered to happen after the exit of a synchronized block. And similarly, a read that happens after the entrance of a synchronized block cannot be reordered to happen before the entrance of this synchronized block. There are additional nuances to the Java happens before guarantee, some of which I have listed in this slide. However, rather than listing every single guarantee throughout all the Java APIs, I will just summarize it with the definition I had in the beginning, that the Java happens before guarantees are all sets of restrictions on instruction reordering to avoid instruction reordering breaking the Java visibility guarantees in various ways. So the Java happens before guarantees exist in order to make sure that communication between threads works correctly. That's it for this video about the Java happens before guarantee. Remember to check out the description below the video for a link to a textual version of this tutorial, as well as other related tutorials. If you like the video, hit the like button, and if you want to see more videos like this, subscribe to my channel, and I'll see you in the next video.